In this video, I will talk about conditional probability and independent events. We write P of A to represent the probability of A, and it quantifies the uncertainty about whether A will occur or not. Now, if we know that some other event has occurred, say B, it may change our assessment of the probability of A. We write A given B, or more concisely, probability of A with a vertical line and then B, to represent the probability that A occurs given that we know that B has occurred. So for example, if we are tossing a die, the sample space is 1, 2, 3, 4, 5, or 6. And let's say A is the event that a 6 occurs. We all know that if the die is fair, the probability of A is just the number of events in A, which is 1, divided by the number of events in S, which is 6, and this is the probability of A, 1 over 6. Now suppose B is the event that we get an even number. Then B is just 2, 4, or 6. And if you want to find the probability of B, that is 3 over 6, or half. Now, suppose we know that B has occurred, which means that we know that the number is an even number. What is the probability that the number is 6 then? Well, since we know that B has occurred, we can represent the new sample space to be just 2, 4, 6, because we know that it cannot be 1, 3, or 5. And so therefore, the probability of A given B is just 1 out of 3. And you find that this probability is different from the original probability of A if we did not know that there was an even number. Now, there is another way to get this probability, and I'll write down the formula here, and later I'll explain how we get this formula. One way of finding the probability of A given B is to use this formula here. It's the probability of A and B divided by the probability of B. Now, the probability of B we found from here is 1/2. And the probability of A and B, so A is just 6, B is 2, 4, 6. A and B is just 6. And the probability of a 6 is 1/6 from over here. 1 over 6. And if you divide this, we get 1 over 3, which is the same as the probability of A given B that we found earlier by using the S asterisk, the new sample space. Right, so sometimes conditional probabilities can be found by figuring out what the new sample space is and then evaluating the probability of an event. Another way of finding conditional probability is to use this formula, in which case we will use the original sample space S over here. Now, so this is the formula that we have for the conditional probability of A given B. And I'm going to draw a picture to sort of explain why this might be the case. So this rectangle represents the sample space S, and I have an event A, let's say it's like this, and I have an event B that is like that. Now, if I want to find the probability of A, remember we can think of it as being the area of A divided by the area of S. Now, what about the probability of A given B? If we know that B has occurred, then we know that the sample space is no longer S. It is actually B. And the probability of A given B is just this part, right? So it's the area of the shaded part, which is A and B, divided by the area of B. Now I can divide the numerator by the area of S, which I erased, but which I can put back. And the denominator, I divide by area of S as well. So the two area of S's, they cancel away, but the reason why I put it back in there is because now the denominator is just the probability of B following the same way of thinking about probability over here. And the numerator is just the probability of A intersect B. So this is a formula that is useful to remember. Finding the probability of A intersect B, it's equals to the probability of A, finding the probability of A given B is the probability of A intersect B divided by the probability of B. Let me write that down again. And if I were to bring the probability of B in the denominator over to the other side, I have a similar formula that is often very useful. The probability that A occurs and B occurs is the probability that B occurs, and then given B has occurred, the probability that A occurs. This is quite a useful formula, and we can think of it by treating A and B as being part of a two-step procedure. So suppose we start from here, and then B may occur or not, and then given B, A may occur or not, and given B complement, A may occur or not. And so this branch of the tree diagram gives you A intersect B. This first arrow here has a probability B of occurring, and the second arrow here is the probability that A occurs given B has occurred, because now we are at B and we want to know the probability that A occurs given B. And the probability of A and B is just the probability of B times the probability of A intersect B, just like it says over here. Now, sometimes A given B is unchanged. This happens when the event B tells me nothing about event A. So for example, A is the event that it rains tomorrow, and B is the event that I ate pizza for lunch today. So knowing what I ate for lunch does not change the probability of whether it will rain tomorrow or not. In this case, the probability of A given B is unchanged. It is still the probability of A. When this happens, we say that A and B are independent. And so A given B equals to PA means that A and B are independent. And very often the way to symbolize independence is with this perpendicular sign over here. Now, if A and B are independent, it means that B and A are independent. So, not surprisingly, A will tell me nothing about B. And so probability of B given A is still probability of B. And so now I'm going to write down some formulas. This is the conditional probability formula that always holds. And there is a second version of this. And you'll notice that there's nothing special about A and B. You can reverse A and B. And so probability of A intersect B can also be written this way. Now, if A and B are independent, then the probability of A given B is just probability of A. Probability of B given A is just the probability of B. And the probability of A intersect B is just the probability of A times the probability of B, using this formula, but with probability of B given A equals to PB. Right? Now I want to talk a little bit about the difference between mutually exclusive events and independent events, because many students confuse the two. Remember, two events are independent if they tell me nothing about the other event. Now, mutually exclusive event means that the two events do not overlap. So let's say this is event A and this is event B. In this case, A intersect B is empty, which can be written this way or this way. And so therefore probability of A intersect B is equals to 0. Now note that this is not the same as probability of A times probability of B. And so A and B are not independent when they are mutually exclusive. Mutually exclusive events do not overlap. And so if I know that A has happened, I am certain that B did not happen. So therefore mutually exclusive events are actually very, very dependent. If you know that one has happened, the other one did not happen. And so they are not independent. It is not easy to represent independence in a Venn diagram, but I will try to show you how we can do that. Suppose this is S, and this is the event A, and the way I've drawn it, the probability of A is 1/3. And now let's say we have an event B that is like this. And we find that if I know B has occurred, the chances of A occurring is pretty small. It's just this part. Right? So the way I've written it, the way I've drawn it, the probability of A given B is quite small. And so in this case, A and B are not independent, because knowing that B has occurred changes the probability of A. Now, suppose I have an event C that looks like this. Okay. In this case, if I know C has happened, the probability that A happens is given by the ratio of this shaded region divided by the area of the purple rectangle. So probability of A given C is the area of A intersect C divided by the area of C, right? And that is the probability of A and C over probability of C. And the way I've drawn it, this is roughly 1/3. So this is an example where A and C are independent. If you know that C has occurred and it's in the purple box, the probability that A occurs is still 1/3. That's all for now. Thanks for watching.